Imagine sending a file directly to your friend's computer. No server in the middle. No upload limits. No cloud storage. Just your machine talking directly to theirs. That's peer-to-peer file transfer. Today we're building the real thing in Java, 6 classes, a graphical interface with swing, live progress bars, and chunked file streaming. 2 people can run this application and send files back and forth immediately. We start with the main class. It's the smallest file in the project. It sets the system look and feel so the application blends into whatever operating system you're using, Windows, Mac, or Linux. Then it creates the main window and makes it visible. That's it. The real work begins in main window. Main window is the heart of the user interface. It extends JFrame and sets up a 1000-pixel wide window titled P2P file transfer. It creates a thread pool for handling multiple connections, a transfer manager for coordinating file sends and receives, and a server socket that listens on a random available port. The layout splits into 3 sections, a toolbar at the top, a split pane in the center, and a status bar at the bottom. The split pane shows connected peers on the left and active transfers on the right. The menu bar has 3 menus: File, Peer, and Help. File lets you send files, open the receive folder, or exit. Peer lets you connect to a specific peer by entering their IP address and port, or broadcast a discovery message to find peers on the local network. Help shows an about dialog. The toolbar mirrors the most common actions with buttons for send, receive, connect, and discover. Every button triggers a method that runs on the thread pool to keep the interface responsive. The left side of the split pane is the peer panel. It has a titled border reading, Connected Peers, a list component showing every connected remote user, and a refresh button. The list displays each peer's unique address. The right side is the transfer panel. It has a table showing every file being sent or received with columns for file name, peer, size, progress, speed, and status. Below the table is a scrolling log area with a monospaced font that shows timestamped events. When main window starts, it immediately starts a server. The server socket binds to a random port, whatever the operating system assigns. This means you never have to configure ports. The local address and port are displayed in the status bar. A background thread loops calling accept, waiting for remote peers to connect. When someone connects, the server reads a peerinfo object from the object input stream, stores it in a map of connected peers, adds it to the list, and launches a peer handler thread to manage ongoing communication with that peer. To connect to someone else, you click Connect. A dialog asks for their IP address and port. The application opens a socket to that address, creates object streams, sends its own peer info, and receives the remote peer's info. Both sides now know about each other. The remote peer is added to the connected peers map and list, and a peer handler starts listening for messages from them. This handshake ensures both sides are ready to transfer files. Not every user knows their friend's IP address. The Discover button broadcasts a UDP packet to the local network containing the message P2P_discover, followed by the sender's address and port. Any other instance of this application listening on port 5556 receives the broadcast and can respond. This is how peers find each other automatically on the same Wi-Fi network. When you click Send, a file chooser opens. You pick a file. If you've selected a peer in the list, it sends to that peer. Otherwise it sends to the first connected peer. The transfer manager takes over. It calculates the total number of chunks by dividing the file size by 64 kilobytes. It sends a file request message containing the file name, size, and chunk count. Then it opens a file input stream and reads the file chunk by chunk. Each chunk is wrapped in a transfer message, sent through the object output stream, and flushed. The sender waits for an acknowledgement before sending the next chunk. After each acknowledgement, it updates the progress bar and calculates the transfer speed. When all chunks are sent, it sends a transfer complete message. When the transfer complete message arrives, it closes the file and logs the saved location. Peer info is serializable so it can travel over object streams. It stores an ID string, a host string, and a port number. The socket and streams are marked transient because they can't be serialized. They're reconnected on each side. Transfer message is the protocol. It has a type enum with 4 values: file request, file chunk, transfer complete, and chunk acknowledgement. Each type has a factory method that constructs the message with the appropriate fields. File chunks carry the actual file data as a byte array. The total number of chunks is included so the receiver knows how many to expect. The transfer manager uses a dedicated thread pool for sending files. The chunk size is 64 kilobytes, large enough to be efficient, small enough to show smooth progress. The format size helper method converts raw byte counts into human-readable strings with B, KB, MB, or GB suffixes. It calculates transfer speed by dividing the total bytes sent so far by the elapsed time, updating every time an acknowledgement arrives. The file receiver creates the output directory if needed and writes chunks sequentially to disk. It uses a for loop counting from 0 to total chunks, reading each chunk from the object input stream, writing it to the file output stream, sending an acknowledgement, and updating the progress display. The file is saved with the same name as the original, preserving the extension. The transfer table has a custom cell renderer for the progress column. It extends JProgressBar and implements table cell renderer. When the table paints a cell, it checks if the value is a string ending with a %sign. It parses the number and sets the progress bar value. This means every transfer row shows a live, animated progress bar instead of just text. When you close the window, the application calls shutdown. It sets a running flag to false, stops the transfer manager, shuts down the thread pool, closes the server socket, and exits. The window listener on the frame ensures this runs automatically. This prevents resource leaks and ensures all file streams are properly closed. You've built a complete peer-to-peer file transfer application with a professional swing interface or even a distributed hash table for finding peers across the internet. The foundation is solid and entirely yours.